Понятия много.
Угу. Так, ну что, все хорошо теперь? Так. Угу. Нормально? Видно, слышно? Хорошо, а звук? А звук есть? Ну, я не знаю, как бы, я хотела уже потихонечку начинать. И что? Хорошо. Вот. Okay. Then we begin our today lecture. And now we start with devices. I think I should give a brief recall of what are devices on algebraic varieties. I'm very sorry for those who already know this. And then we will start with devices on toric varieties. So, first of all, today x will always be normal. First, I state some statements about devices, and in all these statements, I assume that my algebraic variety is normal. What do we need? First, I say that a prime divisor is a subvariety of codimension 1 in X. A prime divisor is an irreducible subvariety such that dimension of D is dimension of X minus 1. One more assumption. I always assume that X is irreducible. So
when you say algebraic variety, you don't mean irreducible, yeah?
In general, I don't mean irreducible, but in fact, when we pass to toric varieties, everything will be normal and irreducible. Just for people who are not very well acquainted with devices, I recall basic notions and give some examples.
Why do we call it divisor? I mean, does it divide something?
Okay. Given any such subvariety, you have order of vanishing. Okay, I maybe start with an example.
We have P1 and we have two primes in P1. Listen to
Okay, I give all the. As I said, a prime divisor is a codimension 1 subvariety.
prime.
Yes. So examples A1 and P1. Okay. In both cases, any point. I say P1. No, I say A1. And here any other point A1 where A1 is either a complex number or infinity. Works well. This is a prime divisor. Okay? We will have many different kinds of divisors. So first of all, this is prime divisor. What for do we need it? If we have a function f a non-zero rational function Cx star. I think I will not prove all the properties, but I just say that we have the order of vanishing nu along D of f is the order of vanishing. So in fact, this is a discrete valuation on this field, on the field of all rational functions on X. And we will use the properties that it is the discrete valuation and the consequences of it. For example, the functions which map to 0 via nu, they are invertible. Okay, I define the prime divisor. Then I can say that formally we say that the group of wild divisors we can take the free abelian group generated by all the prime divisors. Define so it is just the free Z module free abelian group generated by the prime divisors. So it is huge, but nevertheless. And usually it has different notations. In Cox, it is denoted by just div x. But in many other books, it is denoted by w div x. What else? Given any D which can be decomposed as some finite sum a I d I from the group of wild divisors on X. We say that the support of this divisor is just the union of all the i's. The union of the i's for the coefficients which are non-zero. Okay. And what else? What else? Given any rational function on our variety, f from Cx star. I want to say that we can associate a divisor with this function, which will be informally saying the set where this function cannot be defined. So the for this, we can just say that given any f for any prime divisor, d prime divisor, we can check whether it belongs here. So for each prime divisor, we can restrict f to d. There are two cases. Either it is defined somewhere on D or not. If it is defined somewhere on D, it means that it is defined on an open subset of D, because we started with an irreducible variety. If not, so either it is defined somewhere or it is not defined. In this case, we just calculate the order of f along D and say that the divisor of f contains D. And now we can say that for each f from 6 star, there is a finite number of prime divisors D such that nu df is non-zero. Why can we say so? Because there is an open subset where f is defined. So there is u in X such an open subset such that f is regular on U, which means that it maps U to C. U maps to C. Now we can take f minus 1 from 0 intersected with U and say that on this set f maps U prime, f maps U prime to C star, and so support of f belongs to X without U prime. So we have an open subset in X such that all the interesting properties of f belong to this difference. And we know that X is irreducible. Then if we throw out U prime, we get a codimension 1 subvariety. This can be decomposed into codimension 1 irreducible components. So we count the order of f along all these irreducible components, and we get the decomposition. We get that the divisor of a function f is equal to some finite sum a I d I. So for each rational function, we have its divisor given by this formula. AI can be computed as the order of f along di. Okay, maybe if we want an example, on A1, every rational function is just a fraction. For some for I can write x minus a1 etc. x minus an divided over x minus b1 etc. x minus bm. We take all these a with plus and all these b with minus. So this is f equals, we say that divisor of f, it will be equal sum of ai. If they repeat, we just take them with multiplicities, minus sum of bj. So this is how we define principal divisors. We say that a principal divisor is a divisor of a function on our variety. Okay? Maybe on P1. So this is principal divisor. What are principal divisors on P1? So such a function on P1 is well defined if and only if the degrees are equal. We have x minus a1 x minus an divided by x minus b1 etc. x minus bn. And we have some, in other words, we say that divisor of f is sum of ai minus sum of j. In other words, this is just a formal sum of points such that the sum of coefficients is 0. Every such combination is a principal divisor. Okay. Then I think I define what is a Cartier divisor, and we will prove something. People study all these groups because they are very good invariants of algebraic varieties.
So you didn't define what is order of vanishing for that?
I didn't define it because I think if you don't know this, it will be very difficult. And all these basic notions about order of vanishing, about rings which are here, this is written in the preliminary section of Cox, or it is written in any other basic book about algebraic geometry. I think that in any case, if we try to prove all this stuff, there are some steps which we do not prove. In this case, we can say that the divisor D is defined by a prime ideal, and then this is just the localization along this prime ideal. And if we have the localization, maybe you are more or less familiar. How do we define the order in this case? Is it better or not? Do you have questions? Okay. So now, what are Cartier devices? We say that given a whale divisor so given any formal sum of codimension ones of varieties, we can restrict it if U in X is an open subset, then just D restricted to D restricted to U is just if we intersect all the DI with U. This is the same sum AI, DI intersected with U. So it can happen that some divisor doesn't intersect with U, then in this intersection this summand will be 0. And now we say that a divisor is called locally principal I recall that principal is a divisor which is a divisor of a function. And we say that a divisor is locally principal if there is an open covering, the union of some UI, such that for each I, the divisor D restricted to UI is a divisor of some function Fi on UI. Okay? If you know what is a line bundle, in fact, this is the same set of functions. If you have a line bundle on X, it means that there is a trivialization and the transition functions between different charts. These will be exactly the ratios of our Fi. If we have some line bundle on X, it is given by the set of transition functions. And in another direction, if you have a Cartier divisor, the ratios of these functions can be used as transition functions to construct a line bundle on X. Okay. And locally principal divisors, they form a group. So CDX is the group of all Cartier devices which are locally principal. And clearly we have inclusions that any principal divisor is a Cartier divisor. So I didn't write div 0 is the group of all principal divisors. And we have inclusions. We have that div 0x. Clearly, if it is a divisor of a function, then it can be treated as a locally principal divisor. This function will be used in all the charts. So this is in the group of Cartier divisors. And clearly, we defined Cartier divisors as a wild divisor with some properties. Yes, by construction, we have that this is a subgroup here, the group of wild divisors. Okay. Maybe some remarks. First remark is that if X is smooth, then these groups coincide. I'm not going to prove this. I just mentioned this. In this case, equals the group of wild divisors. But in general, they are not the same. In general, maybe the simplest example when they do not coincide is that suppose that we take a x1 x3 equals x2 square. In this variety, this is in A3. In this variety, you take x2 equals 0. So this is not Cartier. I think we can check it in the seminar because this is the codimension 1 subvariety. So this is in the group of well divisors. And now you need to show that you cannot locally give it by some functions. Okay. And now you see that on the examples on P1 and on A1, these groups are quite huge. There are many notions today, but there is no way to avoid it. So we say that two divisors are linearly equivalent if their difference is a principal divisor. Say that D1 is linearly equivalent to D2. No, I say D and D prime. If D minus D prime, what is D minus D prime? This is one formal sum of some subvarieties, and this is another formal sum of some other subvarieties. we just take the both sets. This we take with plus and this we take with minus. If d minus d prime, it is clearly a wild divisor, is a principal divisor. And now we say that let the group of classes of X be the quotient group. This will be the quotient group of wild divisors modulo the principal divisors. And the Picard group, it is the group of Cartier divisors modulo also the group of principal divisors. So from the construction you see that the Picard group is included into the class group. What else? What else? We say that we can consider some examples. On P1, what is the class group on P1? Class group of P1. So we said that principal divisors on P1 are just the combinations of points with zero sum, and the wild divisors is just any linear combination of points. So I state that the class group of P1 is Z. Indeed, for each two combinations of points with equal sums, if we have in the group of wild divisors, we have the sum of A1, D1, and another divisor which is B AI DI, DI. So if they contain different sets of divisors, I can just take a union of them with zero coefficients. If the sum of AI equals sum of BI, these divisors are linearly equivalent, because I can write a function. I just take a function having these points, so some points in the nomenator and some points in the denominator. And if so this is a rational, this is, I can write a fraction. Maybe it is not a function on P1 because its degree will be equal to the sum of AI. I write something like this.
Yeah, but there is degree n.
No. I mean that I'm explaining that the class group of P1 is isomorphic to Z.
Yeah.
So I say that each divisor is a formal sum of points.
Yes.
I say that if the sum of coefficients is 0, it will be a principal divisor.
Yeah.
Because if the sum is 0, I write those with positive coefficients here, and those with negative coefficients I write here. And I obtain a rational function corresponding to such a set of points. And now I want to explain that any two divisors which are not principal, I take this one which is not principal and this one which is not principal, if they have equal sums of coefficients, then they're linearly equivalent.
Yeah, but when you say that you have like there could be it's possible that
No,
Why?
once more. The sum without signs. I mean, there can be if okay, I write in this way: the sum of AI di minus the sum of bi di. Okay. I want to say that this will be the sum of AI minus bi di. Now the sum of these coefficients is 0, and what now? This will be the product x minus di power AI minus by for AI minus bi positive.
What do you mean by x minus di?
We are on P1. Each divisor is a point.
Ah.
I'm explaining the very baby case on P1.
Yeah,
Each divisor
is
is
we have such point.
we have such point. It means that one.
You can always change coordinates.
Yes, we can change coordinate, but
Yeah, but we want to write this function in some coordinates, I suppose. We fix it. No, we always can change coordinates.
so
None of
no,
it's infinity, that's true.
I mean infinity is let us shift in such a way that we have no infinity. You can rewrite it, but I can't write it correctly right now.
No, so suppose you just can change coordinates such that we have only finite number of points. We
Yes.
can always change coordinates such that none of this finite set of points is infinity.
Yes,
Then
this will be better. Shift the coordinates so that
Oh, we can just have two different coordinate chunks.
I just want to write a function. I want to show that every two divisors with equal sum, that they're linearly equivalent. I want to find a function. I want to write it down.
Yeah, but we can have two different chunks and one function and one chunk and one function.
No. I want to have a globally defined function. A rational function, but one for every.
But it's globally defined as long as it goes together.
Mm.
Chunks.
I mean, this works fine. Modulo that we should shift coordinates so that no di equals infinity. It can be rewritten, but I don't understand how exactly. Okay, in this case, this product is divided by the product where AI minus BI is negative. We take x minus di power BI minus AI. So this is the rational function on P1. So sorry.
Like rational functions on P1, this should be some fraction, but the degree on the upper
Yes.
number fraction equal to degree of the lower.
We assume that the sum of AI equals the sum of
but
BI.
that doesn't mean that sum of
It does. One moment. What is?
yeah, of course. Sorry.
Yes.
Yeah, of course, it does.
What is the total degree of this function? This is the sum of AI minus BI plus for positive, and the sum of AI minus BI for those where this is negative. So in total you have this is the sum of A minus the sum of BI, and this is 0 by our assumption. in the very beginning, I said that two different sums of points are linearly equivalent. The corresponding divisors are linearly equivalent if and only if these sums are equal. So I have explained that the class group on P1 is equal to Z. Okay. Okay. Now I think I want to use the two facts also from commutative algebra without proof, and I want to explain how can we find the class group of an algebraic variety. So the first fact is oh no, one fact suffices. Fact. Take suppose that R is a unique factorization domain. Is a unique factorization domain, and suppose that X is spec R. This is, for example, the case when we have the polynomials in variables, in n variables, or if we have if we assume that all these variables are invertible, we take plus minus 1. Then we have either the affine space or the torus. Then first of all, every codimension 1' ideal is principal. If you know all these words, you can easily prove this. Just using that, we have unique factorization. And as a consequence of this, we say that the class group in this case will be 0. I want to use this without proof. Because in this case, all the prime divisors, they will be linearly equivalent, and this will be true. So, as a consequence, we use without proof that the class group of the complex space is 0, and also that the class group of the n-dimensional torus is also 0. Yes. The important is that in the other direction, each Weyl divisor will be in fact a divisor of a function. Okay. And now the theorem. Sorry, can I use the left and right blackboards? No? Okay. Okay, then I erase. Then I erase the the theorem, this is still not Toric theorem. This is in any case. So we take a U, a non-empty open subset in X. And let D1, etc. ds be irreducible components components of x without u that are prime divisors. Then we have the exact sequence. The formal sum zdj, which is mapped to the class group in such a way that each divisor is mapped its divisor class. And then it is mapped to the class group of U. Here each divisor is each value divisor is just restricted to U.
It's not trivial.
Both maps are not trivial.
So you cannot just restrict the di.
Our main so
We need the line.
or maybe I draw something. Maybe I draw something.
This, I suppose, is just intersection.
But
Yes, intersection.
It's divisor.
Okay. No, I write restriction.
The image
So
of the eyes will be 0.
yes. So I draw a picture. We have. So we have A2.
maybe we can perform this.
No. I mean, suppose that you have A2. You have one divisor and another divisor, and this is U. What can be the divisor? Either it is supported on to these lines, or it has another component.
What is U?
U is x1 non-zero and x2 non-zero.
No, it's just
Okay.
everything between the cross.
Yes, if we throw out the cross. So we have this is D1 and this is D2. I just mean that if you have a divisor which is somewhere here, which intersects U non-trivially, then we just take the corresponding divisor in U. And if this divisor is supported on D1 and D2, then it will vanish. So
Yeah, but Leonie said about we have classes in CL of X. We have classes of divisors, and that means that D1 we can just transform it to something that intersects with U, just because it's class.
That the theorem claims that it is zero.
Yeah.
one moment.
Just not trivial.
One moment. Since we assume that x is irreducible, we have that the rational functions are the same. So if you quotient by some principal divisor here, you can quotient by the same principal divisor here. So at this level, everything is correct. Once more, we use that the rational functions are the same. This is the divisors modular principal divisors, and this is and in fact principal divisors are also the same. So at this level everything is okay.
Divisors are not the same.
Each rational function.
Rational functions are the But,
Yes.
The set principal divisors cannot be reconstructed from set of functions.
If you have a rational function that makes two divisors here equivalent, then it can be treated as a rational function here. Surely you lose something on this step, but you lose exactly the components di. The only thing that you lose. Okay, this is our theorem, and I'm going to try to prove it.
Theorem stated that this is exact.
Yes, then it is exact.
It's not necessarily left exact.
Sorry?
It's not necessarily left exact.
Yeah, of course.
Not necessarily left exact.
Because it's
Because there can be some torsion.
Yes.
I suppose the usual.
Sorry?
I suppose we will see it in.
Yes. There will be different examples.
seminar.
Yes. Okay. I raised the example. What should we need to prove? First of all, this composition is trivial. No, which one? First of all, this map is surjective because it's surjective because if we have any divisor on U, we can di prime ai on U, we can take the same di prime in X and take their closures in X. Di prime bar, its closure in X, and then the sum of ai di prime bar maps to ai di prime via this map. Okay, then the composition of two arrows is 0. The composition of these maps is 0 just because this is a divisor in this group, and if we restrict it to U, everything vanishes. It is tricky. And now we take any divisor which maps to 0 here and want to prove that it is of this form. So take the class of D, be in the class group of X such that it restricts to 0 in the class group of U. Then we know that it is a principal divisor on U. Then D on U is a divisor of some function. Of some function which is rational on U for a non-zero function. But since the rational functions coincide, we get that the divisor D minus divisor of this function is 0 on U, and it is a general fact that if this divisor is 0 on U, then it is supported on the union of the i's on x without U, which is the union of the i's, and hence it is a formal sum of these di's. Once again, we said that if in the class group of U this divisor is 0, then this is a divisor of some rational function. This rational function can be treated on the whole variety x. We get a divisor such that on U it is 0. And now we say that it is supported on the union of the i's, and hence it is a formal sum of the i's. And we proved the exactness in this term. And so we have proved this theorem. Okay. And now I think we should pass to devices on toric varieties. What do we have on toric varieties? First of all, maybe one non-obvious thing is that on toric varieties we use only the T invariant divisors. So we just consider only such devices, and it suffices in most cases. Invariant devices on So what is the essence? Usually the class group is highly difficult to compute. But for toric varieties, using something like this, it can be computed. And
Yes. So why everything that we already proved is still true when we consider T invariant divisors?
Just what did we prove? The only thing that we proved is this one.
Well, we also talked about class divisors of Cn and Tn. So, but they're still 0. It seems.
yes.
Okay.
The only theorem that we proved is this one. So to use this theorem, just we say that if we take U is the torus, and this is our variety, and this is our complement. So if we can find this group from the exact sequence, then more or less we are done. Just we used the good fine open subset, which
Yeah, but why it's so true
when we define the class group and the Picard group, we do not say that we use only toric varieties. But to compute them, we need to have some exact sequences.
Yes.
If our exact sequences will be more or less toric in some sense, it suffices to find these groups. We don't say about toric Picard group or toric class group, no. But in this case, if this part is in some sense toric, we can find it more or less directly. Okay. So first of all, what are the devices? What are the t invariant devices on our toric variety? We said that we had the orbit cone correspondence. I hope that if you missed, you know at least something. We said that our toric variety is constructed using some fan. This is our fan, and for each cone of some dimension, the corresponding orbit is of the complement dimension. So for the origin, we had the orbit, which is the whole torus. It has dimension n, the same as the dimension of our variety. And if we want a subvariety of codimension 1, we need a cone of dimension 1. So each torus invariant divisor, it will be it will correspond to some ray tau array of our fan sigma, and we need so this is lattice n. In lattice n, so divisors d tau. So we have as many torus invariant divisors as we have rays in our fan. And we find a primitive vector here, and we denote it by rho tau. Now, what are principal divisors on a toric variety? Principal devices on toric what are rational functions on a toric variety? These are the same as rational functions on the torus, and the rational functions on the torus they come from characters chi m, where m belongs to the dual lattice M. Okay, but it is just the function and not the divisor, and we need to compute what is the order of vanishing of a function of this character along some divisor. So what is our plan? So we assume as know that if we have a function in C where we have variable x1, x2 plus minus 1, etc. So what is the order of vanishing? Order of vanishing nu x1 equals 0 of the function f. Is it more or less obvious how do we define it? we have some polynomial which can contain x1 only in positive characteristic, or only in positive degree, and x2, x3, etc. in any degree. So order of vanishing is, if we can write f some x1 power nu multiplied by some fraction such that it is not identically, neither this nor this is not identically 0 on this subvariety p q, such that pq not identically 0 on x1 equals 0.
Pardon, but what exactly is order of vanishing?
I didn't define the order of vanishing. I said that in general, if you have a function on an algebraic variety, and if you have a divisor, how do we define the order of vanishing of function along a divisor? If you know commutative algebra, you say that there is a prime ideal corresponding to our divisor, and then there is a ring and its localization along this ideal. And using commutative algebra, you define this order. Okay? And in this more simple case, it is just the degree of x1 which sorts out.
Okay, so which comes out as
Yes.
a rational function.
It comes out as a rational function. It can be positive or negative, and I assume that this fraction is such that this part is not identically 0 on this subvariety, and the denominator too. If they were identically 0, then they would be divisible by x1, and they will be able to push it out.
Yeah, yeah. So, I mean, that's the highest number over x1.
Yes, but it can be negative. If it was sitting here, then u will be negative. Okay. And our lemma is that if we take the character chi m, the order of f, which is chi m along the subvariety along our divisor d tau, it is equal the pairing, it is equal the pairing m rho tau. So once more, what is rho tau? This is the monomial which will be used many times. This is the primitive vector on this ray. What is a primitive vector? This is a vector which doesn't contain any other lattice points. So we take the first point on the ray, the first lattice point on the ray. How do we explain this lemma? So if we started with a primitive vector, then after a change of basis, so this is our favorite trick. If we have a lattice n, we can construct a basis starting with any primitive vector. After change of basis, we say that rho tau will be a vector 1, 0, etc., 0. So this is an integer, there is an integer matrix with the determinant 1, which maps the standard basis of our lattice n to some other basis of the same lattice. And it also acts on the dual space. So by the inverse matrix, it acts on the dual space. We assume that this is rho tau, and we have rewritten chi m. So in the dual basis, now we have that chi m can also be rewritten.
One question.
Yes.
So I understand why d tau should be t invariant.
Yes.
But is any t invariant divisor is sum of t taus?
Yes, sure.
Why?
Every t invariant divisor. So we have the orbit cone correspondence. We say that if something is t invariant, then it is the union of some t orbits. Then the dimension is the biggest dimension of the orbit.
N minus 1.
Yes. So if you take a codimension 1 subvariety, which is t invariant, so we decompose this t invariant set into a disjoint union of t orbits. Then it contains a t orbit of codimension 1. But via the orbit cone correspondence, we know all the t orbits. And if we take its closure, it will exactly correspond to the ray. We indeed use the orbit cone correspondence all the time. Okay. So if we rewrite chi m in the dual basis, I say that the pairing didn't change since we changed bases in the dual lattices according to this pairing. And so the order of vanishing will remain fixed. And now, what is the order of vanishing? What is the order of vanishing? If chi m, what is chi m? This is x1 power m1, etc. x n power mn. This is we have some ambiguity of notation, but I don't want to write both bases. In the new basis, and the new coordinates x, in the new basis, if m is equal to m1, etc., mn, then the character is written in this way, and the order, the new along x1 equals 0 chi m. Clearly this is this is m1, but I say that it is exactly the pairing of rho tau. So in the new basis, it is true because rho tau has coordinates 1, 0, 0, 0. And if we take a standard scalar product with m1, etc., mn, we obtain m1. And now I say that when I change my basis, I did it according to the pairing. And so this formula remains true in the initial basis. So I can write all the principal divisors. So I think I erase the proof of the statement. So the result of this calculation is that the divisor of chi m is the sum over all rays of m rho tau, of the coefficient at the divisor d tau. So what do we need to say? We need to say that the difference x set minus the torus is the union of d tau. And we know that the function, the character chi m is non-zero. Chi m restricted to t is in cis-char. So from the general facts, it is true that if the rational function is non-zero on t, then its divisor is supported outside the t. So the support of the divisor chi m is in the union of d tau. So you see, this is the point where everything becomes toric itself. We took the character chi m, and for it the divisor is automatically t invariant. And we know the coefficients. So it is supported here, and the divisor of any rational function is just a sum with some coefficients of one-dimensional subvarieties where it is supported. And we use that formula, and we say that div chi m is the sum of m rho tau d tau for all the rays. Okay. And I think that now I will state the formula which we can use in the seminar, and I will prove it next time. So the main formula which we need is if we know that the fan contains a cone of full dimension, sigma of full dimension, then we have the exact sequence. The following sequence: 0 maps to M, maps to the group of t invariant devices on our variety X, then it maps to the class group, and then it maps to 0. Okay. Let us prove this formula next time. It can be obtained as a corollary of this, but I think that it is enough for today. Okay?
I don't know what was the proof of this lemma.
Sorry?
What was the proof of this lemma?
The proof of this lemma. It was geometric. If we have a lattice, we can make a change of basis in the lattice. So are you familiar with this?
Yeah.
So we take an integer matrix with the determinant 1. The main statement is that taking a primitive vector, taking any primitive vector from the lattice, we can construct a map sending this primitive vector to the basis vector. I want to take 1, 0, 0, 0, etc. And in this case, the order of vanishing along the corresponding subvariety, the subvariety was d tau, and now d tau becomes a t invariant divisor corresponding to this array. So there is an affine charge which is corresponds to this cone, and in this chart this will be exactly this one. So in this chart now we say that the order of vanishing can be computed as m1, but in invariant terms m1 is just the pairing with this. Okay, so thank you. Any other questions?
Yeah. So we find d tau as the closure of orbit of tau, yeah?
Yes.
Okay. And
It is
you say that there is no other divisors that looks like not equal to some d tau, yeah?
any irreducible subvariety of codimension 1, which is t invariant. It is one of our d tau.
Yeah, so by orbit Hall correspondence, I understand that if we have such subvariety, there exists at least one tau such that d tau lies in such y. So do we know that if we have something that
But
so
each di is irreducible.
it's d tau?
Each d tau is irreducible. If we take a union of 2 d tau, it will not be irreducible.
Yeah, but if we have a union of d tau with some d sigma where it's not a divisor and sigma.
But we
has-
know what is the closure.
Yeah.
Okay, we have a t invariant subset.
Yeah. So some variety y. Some variety y. Okay.
We have a if we have a subvariety which is t invariant, it has an orbit of maximal dimension of the torus. We can take the closure of this orbit, and it has a description in the terms of order cone correspondence.
Yeah.
You take the cones which contain this tau. Do you remember this?
Yeah, actually, I understand already.
Okay, so I finished for maybe for other people. If we have any other cones which we didn't list here, then our subvariety will not be reducible. If we take the closure of the maximal orbit and it is still not our subvariety, then the remaining part will be the other irreducible component. And so it is not possible. Okay. Any other questions? Okay, then thank you. Остановите трансляцию тогда. Что? Sorry? I think that today we will have a seminar to discuss how to